All right, I wanted to go ahead and do the free body diagrams for this worksheet that we did in class to make sure they're all kind of on the same page. So remember, each object when you do free body diagrams should always be represented as a point mass. So I'm just going to actually go ahead and draw those now. And people made a really, really good point in class. A lot of people brought this up. They were like, Mr. Abdullah, since all of these things are on Earth, shouldn't we actually have a gravitational pull for every single object? And that is absolutely correct. So we're going to actually have all of these things have gravity here. And here's the thing, based on our little conclusion here, there's a couple things that we're going to actually end up changing based on the lab that we did in class on the last day of class. So here we go. I'm going to have here the weight on this mass due to the Earth pointing downwards, and I'm going to do a little something here because I am actually using this program. What I can actually do is I can go ahead and actually just cut and paste weights to every single one of these problems here. So I'm actually going to just go ahead and do that and kind of take care of that now because it's just an easy way to get all of this done. So every single one of these. Now, I don't recommend you solve it this way on the test, but I'm just saying that if you are kind of reviewing this, just be aware that every single one of these things has a weight, and I just want to get that on here now. Okay, so every one of these objects has a weight, and so we want to get that labeled on here. So that's good enough for now, and I'll continue doing this as I go on. So now here, we have the first object lying motionless. Of course, we did this one in class, and what we ended up having was that we have a normal on the mass due to the surface of the floor. Now here, the second object here, we have a normal on this mass due to the surface. But now, here's the weird thing now, based on our knowledge of what we did in lab. This situation is almost exactly like this is like the dry ice situation. So this is kind of like a piece of dry ice. And here's the deal. What we noticed was that when that dry ice was moving to the right, we had stopped pushing it. It was moving because it was already moving before. And what that means is, since there's no friction to slow it down, there isn't any kind of mysterious force of moving. We absolutely destroyed that idea in lab last time. So there's no force of moving. This stays exact. The free body diagram here and here are identical. The difference is this is not moving and this is moving at constant velocity. It would take a force to stop this and it would take a force to start this one moving. Now there's a slightly different situation in number 3. Here we have the normal due to the surface, but I gave you a rule for friction. The box is moving this way, and we said friction always points opposite to the direction of intended motion. So it's like that. Okay. Now, for number 4, the object slides without friction, so here's what I'm going to do. I'm going to take the perpendicular to the surface. Remember, the normal force always goes normal to the surface. That means perpendicular. So I take this guy, I put it here, and then I draw the normal force as the normal on the mass due to the surface, like this. Okay. Moving on here, I love how people just simply drew their tensions. We have T1 and T2 like this. Same with here. We have, once again, we have, you know what, I'll just redraw it. We got the weight on the mass due to the Earth, but now we also have a tension here and a tension here, just following the rules that we had in class. Now for this one, we have, again, the weight pointing down like this. What else do we have? Again, tension, the rule is it always goes away from the object, so we have a tension here. And of course, we have a normal force perpendicular to the surface. Notice weight always points straight down. Earth doesn't care that you're on a surface. Earth just pulls stuff to the ground. Now for here, we've got one surface here, so I'll call this surface 1. So I'll call this, or you can call this the wall, and you can call this the floor. So if you want to do that, I have the weight going down, and now I have the normal on the mass from the wall and the normal on the mass from the floor. I don't care how you named it, but you want to give these things 2 slightly different subscripts. Now, Moving on here. Wow, it's just great how we can do these problems, because now we have the free body diagram to help us. This is what we call a given force. So I'm just going to copy here, call it F. Once again, normal on the mass due to the surface, weight on the mass due to the earth. Here, once again, don't try to improvise. You've got an F like this and a theta. Copy all of that. We're going to understand what it means next semester. And you have the weight of the mass due to the earth, and you have the normal on the mass due to the surface of the floor. This one's an interesting one. People were confused. Let me show you the trick. This is the mass. I'll call it M. This is the pulley. I'll call it P. Let me show you the free body diagram for each object. For the pulley, I'll do it blue, the mass in red. So here's the deal. For the mass, I have the weight of the mass due to the earth. And here I have a tension from a rope. Just call it T and draw it like this. Next semester, we're going to talk about the relationship between F and T. But for this pulley, you notice we have this force pulling the pulley down. We draw an F like that. And we also have, somehow, the weight of this pulley pulling down. Okay. Now, one thing I will say is that there's probably a nail supporting the pulley or holding it up. But for now, we're just going to draw it like this. And I'm just going to put here a dotted line saying next semester we're going to have to worry about some kind of force that keeps it still. Here, I saw some great drawings. You want to draw your free body diagram like this, though, for the force. Like, take this arrow. Like, if I had this arrow here, you have it. Okay. Don't try to do anything fancy with it. In fact, let me just get rid of this arrow. So I kind of traced over the arrow. What you do is you take this and you actually draw it down on the bottom like that. Okay. And then your angle theta, you can draw it like this if you want. And that's F. And then, of course, we have the normal on the mass due to the surface, and we have the weight of the mass due to the earth. Okay. Now here, the object is falling with no air resistance. Once again, this is still like the inertial problem we did before. We have the weight of the mass due to the earth moving what we realized, what we learned, what we observed in our lab, on our last lab of the day, on Thursday or on Friday, depending when you had block, was moving is not a force. Moving is just something that happens. You need a force to get things moving, and you need a force to stop things moving. That's it. Now here, if you have something falling at a terminal velocity, what's happening is you have the weight of the mass due to the earth, and now it's moving at a constant speed. So here's an even weirder idea. If it's moving at a constant speed, we ought to realize, hey, when things are moving at a constant speed in a straight line, there's no force acting on it. So clearly we have gravity acting. So that means there must be something counteracting gravity in order to balance it, and that is the force of air resistance. So there's a force on the mass due to air. And here, ball rising, parabolic trajectory, doesn't matter, gravity. And here, same idea, gravity. The motion has nothing to do with the force. These things here, these three things, all relate to lab. So this is the part where you really have to, there really truly is no force of moving. And it's very interesting that we've seen it in lab, but I can guarantee after drawing these free body diagrams, the exact, direct, precise connection between this and lab may still be a little confusing for some of you. And that's the part where you need to sit for half an hour with your lab, with these drawings, and explain to yourself exactly how and why this connection is and how it works. Okay, so you have to do that for yourself, and that means you have to sit with the diagrams and sit with the thing, and this may take you half an hour, 2 hours a day. That is the work I'm expecting you to do. I can explain it to you a zillion times. I can't force you to actually understand that connection. That's something you have to do for yourself. So, sorry to kind of leave you on such a grim note, but that really is how you have to understand this stuff.